I'll be presenting the last presentation, which is about green RF amplifiers for wireless communication systems. The outline of the presentation starts with a brief introduction to the motivation behind using new technologies for power amplifiers. Then we explain the general theory for switching mode power amplifiers, which is a new efficient type of power amplifiers. Then we'll move to describe the different steps of designing a particular case of switching mode power amplifiers, the inverse class F. So and finally we provide different examples of design. So through the last years, we saw the evolution of wireless standard to cope the need for high data rate. So we moved from second generation that provides different around 20 to 30 kilobit per second to third generation that provides up to 4 megabit per second, and then with the fourth generation we reached tens of megabit per second. The tendency is to move for the next generations and provide gigabits per second throughput. But this increase in data rate is accompanied with an increase in dynamic range of the signal. That means the signal amplitude varies quite highly, and this imposes stringent constraints on the design of the transmitter. So here we have different typical characteristics of a transmitter, and we see that it's not working. But anyway, for the high input power region, we have the green curve is the efficiency curve, and at this region the efficiency is higher. But the problem is if we look to the blue curve, which is the gain versus input power, at this region we have nonlinear type of response which generate distortions that degrade the signal quality. And if you want to move to the low power region, at the left side, we have a linear response, but the efficiency, the green curve, degrades considerably. The efficiency is the amount of power that's delivered as a useful power. So the higher the efficiency, the less energy loss we have in the system. And we have interest to increase this power efficiency. This is very critical in wireless communication systems. And here are some figures that show how important is this. For example, for a large wireless network operator, it consumes about 3,000 gigawatt hour per year. And this will cost around $370 million per year. In a worldwide scale, the consumption is about 61,000 gigawatt per year, which is equivalent to 33 million tons of CO2 gas emission. From this power consumption, 50% of the energy is consumed in base stations of the wireless network. And 40% of this is consumed by the power amplifier itself. So it's very important to reduce the power consumption of this power amplifier. There are different ways to reduce the power consumption, either on the organization of the wireless structure by optimizing the network layout and deployment, by operating the base stations in sleeping and awakening mode to reduce the power consumption when there is no traffic. We can move to optical switching equipment that consume less power, and we can propose power efficient base stations. How to do that is to reduce, one way is to reduce the power usage of radios and amplifiers. And this is what have been done through the last 20 to 30 years. We start with quite linear type of amplifiers that provide an efficiency about 10%. Then we move to improve the efficiency by moving to a more nonlinear and apply class AB and applying a linearization technique. First, people proposed feed forward that improves the linearity but not match the efficiency, and then they propose a new linearization technique, digital pre-distortion or DPD. Now, currently in industry, we use Doherty amplifiers that are more efficient but provide more nonlinear behavior. But with digital pre-distortion, we can compensate for this nonlinearity. The tendency is to move for digital transmitters and use switching mode power amplifiers that are much more efficient. Why that? Why is that? Because if we look to the curves of the drain current versus the voltage, the drain voltage, switching mode power amplifier consists in operating in the high efficiency region where there is either current and no voltage, or there is voltage and no current. How to achieve that? If we can somehow configure the transistor to mimic a switch behavior, that means either open a switch and we have zero current and high voltage, or off or on, we have high current and no voltage. The product of the current and voltage is equal to 0 at each time. And this means that there is no power dissipation and 100% efficiency. There are different ways to achieve this switching behavior for the transistors. One way is to the inverse class F power amplifier. And this consists on tuning terminating the transistor in a way to achieve a current waveform of a square wave and half sine wave for the voltage. If we plot the power series for the two waveforms, we see that the current will contain only the odd harmonics and the voltage will contain only the even harmonics. So by terminating all the even harmonics to an open circuit and all the odd harmonics to a short circuit, we can theoretically achieve this behavior. In practical, we terminate only two harmonics, the second and third, because it's impractical to have an infinite number of harmonic termination. And this can allow us to achieve a theoretical efficiency of 90%. This is an example how I achieve this harmonic matching network. So we have two stops for the harmonic matching and then a fundamental matching network with transmission line and a stop. For the harmonic matching, each stop is for one harmonic. So it transforms an open circuit to a short circuit at the intersection, and then with transmission line we tune the harmonic termination to achieve the best performance.